Hi, this is Reese. I'm going to be completing a final problem in Intro to Mechanics class. The problem is a projectile is fired at a speed of v naught with an angle of inclination of theta from horizontal. When it reaches its maximum height, the projectile explodes into two equal mass pieces. Right after the explosion, one piece travels forward horizontally at twice the speed of the other piece that is projected backwards horizontally. How far from the launch position does each piece land? All right, so there's a lot going on there. I started by diagramming. So this is the diagramming for the situation. We have the projectile with an initial velocity fired at angle theta, and then when the projectile reaches its maximum height, it explodes, and that has a coordinate in the x direction and in the y direction. The amount of time the projectile takes to get to the explosion is the exact same amount of time that it'll take these two particles to reach the ground. That goes for any particle. The projectile fired backwards is traveling at 1/2 the speed of the projectile fired forwards. So this is the new velocity, and this is 1/2 the new velocity. First thing we want to do is get the coordinates for this explosion. That's our first step. We want to know where that's at. So we're going to use a kinematic equation to solve for the x position first. So this says that x final is equal to velocity times time plus x initial. So we're going to call x final, x position of the explosion, E, is equal to velocity in the x direction times time plus initial x position, which we'll just call x. Okay, now what is velocity in the x direction? Well, this right here is a vector. That is traveling at an angle. Technically, there is velocity in the y and in the x. So we can represent that. So that's our vector, okay? That's the velocity. That distance right there is the velocity in the x direction. This is velocity. This is the velocity in the y direction. Right now we know this, and we know this is theta. We know from trig that cosine of theta is equal to the adjacent side of the triangle over the hypotenuse. All right. So adjacent over hypotenuse, this is the adjacent to the angle, this is the opposite, that's hypotenuse. So adjacent Vx, hypotenuse, initial velocity. Multiply both sides by initial velocity to get velocity in the x direction by itself, because that's what we're looking for. So you get initial velocity times cosine of our angle is equal to velocity in the x direction. So then we can say the position of the explosion in the x direction is equal to v naught, right? We're just plugging this in to that. V naught cosine of theta, and then t, where that t is just going to come right down, plus our initial position, which is right here. All right, so now we have our position in the x direction. We're looking for the position in the x direction of the explosion to make sure that this makes sense, because what the heck is that? We don't really know. To make sure that makes sense, we can check units. So this is distance, meters. V naught is meters over seconds, right? You're traveling at meters per second if you have a velocity. Cosine of theta is nothing. V naught times seconds is seconds, because that's time, plus a distance, which is meters. Okay, s's cancel out. You have meters plus meters, which is equal to meters. So that checks out. Perfect. Okay, we can break this problem into two parts, the x and y direction. So we're just going to continue with the x direction. So the projectile travels here, it's exploding, and then splits into two. And it goes right, and it goes left. These two particles. All right, so where did those land? You can represent where they landed with two equations. So we're going to start with the one that went forward, right? So the one that was on the front side, it has a new velocity. So we're going to say velocity new. And then we're going to use the exact same kinematic equation. So the new position in the x direction is equal to velocity times the amount of time that it's traveling plus its initial position. Where's its initial position at the explosion? Explosion E, or x of E, right? So now our initial position is at the explosion coordinate. Perfect. Now we have our backwards one, the one traveling backward. Okay, so let's just say this is the exact same thing. So the problem says that the one going forwards is traveling at twice the speed as the one traveling backwards. And since we said that its speed is new velocity, then this is just simply going to be 1/2 new velocity. Because this is traveling twice the speed, this is traveling half the speed of new velocity. So 1/2 velocity new plus its initial velocity is a good equation for that one. All right, so now that we have the equation of... All right, so again, the question is asking, where did these two particles land? How far away from right here did they land? And with these equations, it kind of represents that, right? We know that this is going to land here, and this is going to land here. We can solve for those with these equations, but we need time, right? We need to figure out what time is. There should be a time in here. Yeah, so we need to know what time is. Okay, to figure out how much time it took from the projectile to get from here to explosion, we need to know the y value of the explosion. So, we're going to call the y value of the explosion y of E. Y explosion. All right, the kinematic equation that's going to be helping us with this part of the problem is v squared is equal to v naught squared plus 2a times change in distance. Okay, in our case, change in distance, so change in distance is equal to d final minus d initial. That's how you find change in distance. If our initial is 0, right, if we're starting at 0 meters, we can just say that change in d is equal to d final. D final is just distance. So we can just say this is distance. That makes it easy. And then to put it into our circumstances, we have Vy, because we're talking about the y axis now. So the velocity in the y direction squared is equal to the velocity, the initial velocity in the y direction squared plus 2. What's our acceleration? Well, it's starting with an initial velocity. It doesn't have any propellant, so there's no acceleration. It's like pushing it upwards, but there is an acceleration on it, and that's just gravity, because we're assuming this is on Earth. So gravity is 9.8, so that's just g. All right, and then times y, because that's our distance. We're trying to find the y value. We can say y of E. The y value at explosion. All right, now how can we make this easier? We're looking at the max height. That's where the explosion happens. So the max height. When something is traveling up, 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 and then it starts traveling down, 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 down. For a split second, it stops. So up, 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 down, down, down. So the max height, there's 0 velocity. So that's really easy. Makes it equal to 0. Gravity is negative. So let's say that's negative 2g. Okay. All right, so now we have 0 is equal to v. Initial velocity in the y direction squared minus 2g. That. So we're trying to isolate that. So let's just start by adding it to both sides. We get 2gy is equal to v naught y squared. All right, so the initial velocity in the y direction. What the heck is that? Well, we can make that same triangle. So initial velocity is a vector. That's initial velocity. Then remember we have velocity in the x direction, and we have velocity in the y direction. These are all initial velocities. So we want to figure out what velocity in the y direction is equal to. Okay, so here's our angle right here. So sine of an angle is equal to opposite over hypotenuse. that's helpful for us because the initial velocity in the y direction is opposite. So we can say hypotenuse is v naught, and then we multiply v naught by both sides to get the cancel on this side, and then equal on this side. So in other words, v naught sine of theta is equal to vy naught. We've got a vy naught right here, vy naught right here. I just have them flipped. So we can say 2gy, plug that in, v naught sine of theta. Perfect. Now we can divide both sides by 2g. That cancels 2g on this side. So then we get, I'll write down here. So then we get y, the y value of the explosion is equal to the initial velocity times sine over angle squared over 2g. Cool. That's everything that you can solve for because it says it has initial velocity. Again, we're not using numbers, but if you were using numbers, you'd be able to plug that in and get a number. So that's basically constant. So that's awesome. And just a minute ago, we solved for the x position of the explosion. That got erased. So let me throw x position of the explosion is equal to v naught, the initial velocity times cosine of theta times t. So there we go. We have the position in the x direction and the position in the y direction. So now we have a coordinate. When you have the x and y position, you have a coordinate. We know exactly where that is. We no longer need all this. So look at that. That's where we get our location for the explosion. Looks like that checks out. Yep. So you have your y coordinate and you have your x coordinate. Those are the same things. So I wrote this beforehand because I solved it on paper first. Wanted to make sure that checked out while I was solving it on the board. Perfect. This is the initial velocity in the y direction. And if you remember from earlier, we said that is equal to the initial velocity times sine of theta. All right, and then we have the y value of the explosion down there. We have that right here, so let's plug that in. That's initial velocity times sine of theta squared over 2 times gravity, and that's equal to this, negative 1/2 g t squared plus initial velocity. Okay, and then I used, to solve for t, I think you only have to, I think you have to use the quadratic equation to solve for t. So if we set this equal to 0, move this over to the same side, we have 1/2 g t squared plus, well, this has a t right here. So v naught sine of theta t. Move this over to the other side, and we got minus v naught sine of theta squared over 2 times g. Okay, this is in quadratic form. You have squared, then you have single, and then this is a, b, and c. So we can use the quadratic formula. It's going to be b plus or minus b squared minus ac over 2a. And we got a, b, and c. All right, now we need some more room. So it's like, well, doing the product formula, t equals to g over naught sine of theta plus minus. Okay, and then we'll velocity. All right, and then we'll make 0, 0 times 0, so 0 over 0 is 0. So we got g equals to this. Awesome, time. All right, yeah, we get. So we can use this equation, pull it up here. The x final of the particle that is shot out in the front. So x final position is going to be the new velocity times time, right? Times time, and it's v naught sine of theta over g plus xe, which is v naught sine, or we can just say xe. That's the most simple form that's going to be. All right. So there's 2 here. So this right here is the same as our Vy. So we can just say x final is equal to Vy over g plus xe. And that 2 stays in there. And then the x final for the one going backwards is equal to 1/2 new velocity t plus xe. So x is backwards final. So backwards final is equal to negative 1/2 because it's going back, times 2 times v naught sine of theta. This is over g. So v naught sine of theta, if you remember, that is our initial velocity. That is our velocity in the y direction. The 1/2 and the 2 cancel, so then you're left with there's an xe over here. So these cancel, you're left with xe minus vy over g. All right, let's check to see if these two answers make sense. Well, they both have a b value of the x position of the explosion. That makes sense because that's where they started. Right here. Right, they're starting here, one's going forward, one's going backward. The one that's going forward is 2 times the velocity of the one going backwards. That makes sense why there's a times 2. And this one doesn't have a times 2. Okay, now this one's going forwards. Its x value is increasing, so it's positive. That makes sense. And this particle is going backwards. It's getting closer to 0. That's what makes sense why it's decreasing. So those answers make sense to me, and that's my answer to my final question of Intro to Mechanics.